Hello! In this video we will see how to solve problems with energy when some of the mechanical energy is lost. Previously we have talked about kinetic energy and potential energy, where kinetic energy is the energy associated with the object's motion, and potential energy is the energy associated with the object's position. Because these energies are related to the way an object is moving, they both fall under the category of mechanical energy. Mechanics is a term for how things move. Other energy types, like heat or light, don't directly relate to the way an object moves and can't be easily converted back to kinetic energy, so they are not included in the category of mechanical energy. Forces like gravity and spring force merely convert kinetic energy to potential energy, and back again. However, the total amount of mechanical energy remains the same, or is conserved. For that reason, we call these forces conservative forces. Other forces, however, like friction, behave quite differently. They will take kinetic energy and convert some of it into heat, which is not a mechanical energy. Since friction and air resistance remove energy from mechanical energy and convert it into something else, we call those forces non-conservative, since the amount of mechanical energy is not conserved. So, for the rest of this video we will work out a problem we worked out before, but this time we will include the effects of friction. Welcome back to our roller coaster. Again, we have our car start at the top of the hill, with a kinetic energy of 1000 joules. We want to know what will its kinetic energy be at position B. In fact, will it even be able to make it to position B? This time there is a constant frictional force of 100 newtons, and the amount of track length between points A and B amounts to 300 meters. Previously we could assume that the mechanical energy at position A would equal the mechanical energy at position B. Put in a more familiar way, that means we could write this equation. Using this equation, we could just solve for the final kinetic energy, and we would get 21 kilojoules, as we saw in the previous video. However, this time, we can't assume that the initial mechanical energy equals the final mechanical energy, because some of that energy is lost due to friction and converted to heat. So really we'd have to write this equation. Initial mechanical energy minus work due to friction equals the final mechanical energy. This way we account for the loss of mechanical energy. Again, let's write this in a more familiar way, and then we solve for the final kinetic energy, which is just a matter of bringing one term from the right over to the left. Now, before we plug numbers in, we should probably calculate what the work due to friction is. Work equals the frictional force times the distance. Now, the frictional force is 100 newtons, and it acts over 300 meters of track. So we plug these in and get 30 kilojoules, which is 30,000 joules. Finally, let's plug in the numbers and see what we get. Recall that potential energy of gravity is mass times gravity acceleration times height, and I will treat gravity acceleration as just 10 meters per second squared. After doing arithmetic, we find that, we get negative 9,000 joules. That's weird. What does it mean for a kinetic energy to be negative? Work can be negative because that represents the direction of an energy transfer, but kinetic energy? What on earth does this mean? Well, the truth is that a kinetic energy can't be negative. The fact that it's negative here means the situation we are asking about is impossible. The car was never able to get to position B due to all the friction. It ran out of kinetic energy somewhere on its way back up the hill, and then fell backwards down the hill. Then when it got to this side, it would have run out of kinetic energy yet again, and fallen forward. But this cycle can't last forever, because every time the car moves, friction drains away some of its energy. Eventually, it will be stuck at the very bottom of this hill. Perhaps a better question for us to ask, then, is how much initial kinetic energy must the car have in order to just barely make it to point B? Go ahead and try to work this one out yourself. To solve this problem, we just need to consider the same equation we already had, and this time, solve for the initial kinetic energy. We also need to realize that for the car to just barely make it to point B, that means that the final kinetic energy is 0. The rest of this problem is simply a matter of putting in the correct values and doing the arithmetic. You'll find that the required initial kinetic energy is 10 kilojoules. And that's it for this video. Thanks for watching.